Spotlight session, and our speaker today is Ramesh Sitaraman. Let me do an introduction. So he's a distinguished professor and associate dean at UMass, which is where I am from as well, and his research has focused on internet scale distributed systems. He has done a lot of work on the algorithmic aspects, architectures, performance, energy efficiency, whole set of systems issues. He is most known for his long time effort and pioneering work in designing internet scale distributed systems when he was at Akamai, and he actually designed their content delivery network from the streaming side and many other edge computing services, and he continues to have a role at Akamai. He is the chief consulting scientist there and continuing to evolve their infrastructure, and today's talk is actually going to focus also on his Akamai work. And he's won many awards for his distinguished contributions to the field. He is a fellow of 3 professional societies, the ACM, IEEE, and AAAS, and he's received the SIGCOMM Networking Systems Award for his work, and also the MPEG, the Dash Award for his contributions to streaming, and many other awards as well. So without further ado, let's welcome Ramesh to the podium.
Thank you. Thank you, Prashant. Can everybody hear me? So I've been working on edge-related things really from the late 90s when we first started Akamai and built the first content delivery network, which was really the first edge service. A few years later, we also built the first edge computing service. In this talk, what I want to do is reflect on sort of nearly 25 years of building edge computing and edge services, and also look forward to where things are going from an industry standpoint. I can just start by saying that I've never been more excited about edge computing than I am today. Much more so than we first built it, because I think the time is, sometimes you build technology and the time is not ripe, but now the time is ripe. And I hope that I'm going to focus a lot on the industry side. I'll talk a little bit on the research side also, but I hope that this gives you a source of problems that you can work on, because I think edge computing really needs a lot of help from the research community at this point, because expectations are growing faster than what we can really do. Okay, so with that, let me begin. I want to actually start by defining what an edge is, because there are various different definitions even in this community. And as I've been listening to the talks, I see there are so many different definitions of the edge. So our original definition of the edge is a set of servers deployed around the world. The property that we want for them is that it is ubiquitous. So wherever you are in the world, you are proximal to an edge server. Okay, well, proximal you can define a lot of ways. If you're a networking person, you would say you're 1 hop away from a server. Or you could say you're within like 10 or 15 milliseconds from a server, or however you define it. We want the edge to be ubiquitous. That was our initial conception of what an edge is. And it's different. It's fundamentally different from a cloud. I mean, one obvious difference between an edge and a cloud is that the cloud has far fewer locations. But that's not the only conception. We actually conceived of the edge as being location independent. Okay, the way we think about the edge, even from the early days, is that it's location independent. When you think of the cloud, you think of, I have, a bunch of servers in Virginia, a cluster somewhere else. That's not how you think of an edge. You think of it as just location independent. It's just there wherever you want it. Okay, that's you'll see that as I talk through this. That kind of an ideology. Okay, so you might want to see what an example of an edge is. This is Akamai's edge. Today, I would point out that it's pretty much got 4,000 plus different POPs where servers are deployed. The servers could be a really large, hundreds of servers, or it could be like much fewer as well. The point is that it should be ubiquitous, as I said, right? So it's in pretty much most of the major networks, in most of the major countries, it's distributed everywhere. Okay, so this is just an example, and it obviously has a lot of capacity because it has hundreds of thousands of servers, right? Close to 500,000 servers. Okay, so this is what the Akamai Edge is. So I don't want to delve too much into content delivery networks, but I said that we built the first one back in the late 90s. I will put some dates on the right corner side so that you can get some historical preview of what I'm talking about. So content delivery was really the first edge service, right? So what was the idea of content delivery? You have a core with content. By content, I mean like web pages, videos, so on and so forth, right? The core basic idea that really we started out with is that you can push all that content. Well, if a user wants to access the content, they have to route into the core of the internet to access that content, right? There's many problems, right? You can have performance issues like high latency. There could be reliability issues because there's a single point of failure. And you can have, all sorts of other issues. You have scalability issues because if 1 million people want to access the same content, you can't do that anymore, right? So our initial conception was we'll take the content and push it to the edge, right? Edge is, of course, a set of servers that's close to users. That was the original idea. And we built the edge for that, for that particular purpose, right? But even in the early days, in the late 90s, especially when you're about to IPO, for example, people will come and ask, are you like a one-trick pony? What else can you do, right? But even back then, we used to say, look, this is not the only thing we want to do. We want to push everything to the edge, including the compute, right? So compute was the holy grail of content delivery, right from the beginning, right? It took us a few years to get there, but that was always what we said. That's what we wanted to do. So really, edge computing really evolved as sort of a logical evolution of content delivery, right? If you look at what sits inside, we usually call the enterprise servers as the origin. That's the original, from a content delivery standpoint, that's where the content resides originally. From an edge computing standpoint, that's where the compute and the data also reside, right? So you may have database servers, app servers, web servers, and content delivery just did the first part. It took the web server and the content and pushed it to the edge, right? So the logical next step is to take whatever the app server is doing, whatever the database is doing, and push it to the edge, right? That's really, and that's what basically edge computing is in our conception. Okay, so it's just a natural. It took a few years to do that, but that was really the natural thing. Okay, so I want to actually talk a little bit about the edge. So let's get into this first. So edge computing is really, in our view, just a logical extension of content delivery. And in fact, if you look at the benefits of edge computing, they pretty much line up with the benefits of content delivery, right? So in content delivery, you get better performance by pushing it to the edge. Same with compute. You get better performance. Cost is always an issue. I'll talk about that. Sending something out from the edge is cheap because of the way we built the edge. It's cheaper than sending it from the cloud, for example, right? So cost is always an issue. Scalability benefit. If you host compute on the edge, you can scale if there's a flash crowd. If there are a lot of people wanting to access that particular application, it's fine because you have a huge edge, right? It has the offload benefit, which is you're offloading the client computation onto the edge. You're also offloading the origin and the cloud onto the edge. So those benefits also are there. There's resilience benefits. So really, the benefits, are really just identical the way we see it. Right? It's really the same kind of thing that you get when you push compute to the edge, right? And I also want to say that the way we think about edge computing on the edge is that it's a fully managed service, right? And that's one way it differs from the cloud. There's no such thing as Kubernetes, okay? So our conception, if you look at the content delivery world, you give the content to the content delivery networks, and it decides where to put the content. It decides which servers, how many servers, how to route the users to that content. Everything is done by the content delivery network, right? That's exactly our conception from the beginning for an edge computing service. You give me the compute, I, as the system, as the edge computing system, will figure out everything else. We'll see where the demand is coming from, right? We will actually route users to the right servers. That's called the mapping process. And we will actually figure out where to put the compute, right? How many servers, which locations, everything is done by us. So that's actually what we call a fully managed service, right? So that's also different from what a cloud is. Okay? All right. So I want to actually, when you think of the edge, I think most people just think of the edge, right? But that's not how we think about it, right? And in fact, Akamai is building something like this, right? So when we think of the edge, we think of an outer edge. An outer edge could be like the CDN edge that actually is very pervasive and everywhere, right? I showed you what it looked like, right? And we think of an inner edge, which may be hundreds, instead of being thousands of locations, it could be like hundreds of locations, right? And then, of course, there is a core, which is the cloud. So I like to make the analogy of, this picture being sort of like a memory hierarchy of sorts, where as you go from the outer edge into the cloud, latency increases, right? It's not 10 millisecond latency anymore, it becomes higher, right? But the compute actually gets bigger and bigger. For example, the CDN edge, the outer edge that is, does not have a lot of GPUs. You can imagine, because it was built really for content delivery, and it's also pretty expensive to put GPUs in thousands and thousands of locations. It's actually a pretty bad deal because they get outdated really quickly. I mean, you buy GPUs and you put them on the edge, they're outdated within a year, right? There's something like 3 times faster, right? It's a losing thing. So the edge, outer edge, as we see it, is always going to be less resource intensive, right? But the inner edge could have more sophisticated GPUs and does have more sophisticated GPUs, and of course the cloud does as well. So I wanted to have this picture in mind when I talk about the edge. Okay? All right. I want to actually switch gears a little bit and talk about how edge computing is done, right? And I want to talk about the paradigms of edge computing. Edge computing is not just one thing, but there are different paradigms that people use for edge computing, and we've used over the years, right? I've drawn 3 pictures here, like 4 pictures here, and one is bigger than the other. So the way I think about these paradigms is, how long does the compute live and how complex it is, right? So the first kind of edge computing that we built, I also put some years here on sort of the history of it, when we first built that kind of edge computing, right? The lowest kind of edge computing, in a sense, in terms of commitment, and it's transient. It doesn't live for very long. Is scripting on the edge, where you can write scripts in some scripting language, and it runs on the edge, right? So that's like the first paradigm I'll talk about. The second paradigm is has a little more of a permanent place, which is serverless functions. A function is executed, the compute lives during that period, and then it goes away. Right? It's not super persistent, but it persists for a while. A third paradigm I'll talk about is general purpose edge computing. And general purpose edge computing is running arbitrary applications on the edge, and they could pretty much run forever. Okay, and finally, I'll talk about edge AI as sort of a fourth paradigm, because it merits its own paradigm, because that's really like driving a lot of edge computing today. Okay, so I'll start with each of these paradigms and I'll give you some examples. Okay, so let's start with scripting on the edge. The first time we built scripting on the edge was actually driven by content delivery. So when we were delivering content, it turned out that the content just couldn't be delivered just as it is. You had to actually, our customers said, you got to encrypt it, you got to do this, if that is true, and it became pretty complicated. It was not just deliver this content. There was a lot of customization that we needed to do. And so we invented this language called metadata, okay? It started out this was back in 2000. It started out by being a very simple language that could do compute on the edge. This is a more modern version of that language. This in the simplest form, it just says, if this condition holds, then take this action. Right? That's what this metadata script is doing. This metadata is actually doing something like a firewall, where it says, if you have a client with this fingerprint, then you do something, right? That's what this is doing, right? I'll come back to firewalls in a minute. This is how our journey into edge computing started, by customers really asking for some amount of compute to actually modify the content. Okay, but you know what happens with these things. You get a bunch of software engineers to kind of like look at this and keep working on it. Soon it gets more and more complicated, and we ended up with something that's Turing complete. Actually, one of the software engineers had sort of a theory bend, and they actually proved that the metadata that we currently have is Turing complete, can simulate a Turing machine. Anyway, it became pretty complicated, and it has a lot of uses. I said transforming content is one. You can specify caching rules, how much you can cache. You can stop people from accessing certain things. You can encrypt. You can do add insertions. You can do digital rights management. You can do a lot with just scripting on the edge. Okay. But the thing that I want to actually focus on, which I think is the killer application for scripting on the edge, is what I call edge defense. I would say that edge defense is one of the most important computing things that happens on the edge. So what is edge defense? So I said that CDNs were built like 25 years ago as the first edge service, and soon enough, a lot of people, almost all of the internet, whether you think about application providers, web providers, video providers, they all use CDNs, all of them, right? Like something like 80% of the internet traffic goes on CDNs today, right? And what does that mean? It means that whenever you access the internet, you go to an edge server first, before you can go anywhere else. If you go to whitehouse.gov, you don't even know where it is. You go to an Akamai edge server, for example, right? So the edge has become the gateway to the internet, right? What does that mean? If you are the gateway to the internet, you also have to defend the internet, right? Because anyone, whether it's a good person, bad person, terrible person, malicious person, they all go to the edge, right? So that is what edge defense is. Edge defense is a form of edge compute using scripting, mostly scripting, not completely, that actually defends the internet from bots, from all sorts of malicious activities. Okay? All right. So if I look at the Akamai network today, and look at the edge, there are millions and millions of metadata rules that are being executed that do sort of like a firewalling kind of activity that I showed you earlier, right? So let's talk a little bit about edge defense, because I think it's something that could use a lot of research. Okay, so the edge defense also has some history. In 2001, we came up with this notion that the edge could hide the origin servers from the rest of the world, right? So you could not, as I said, to access anything, you have to go to the edge, and you don't even need to publicize where you are, right? So we call that site shield. So basically, you don't even know where the IP of whitehouse.gov is, right? You resolve it, you get the edge, the Akamai edge, right? So we built this very kind of a very simple service. All it would do is the edge would do things like, if you're accessing it on the wrong ports, it will deny you. Some simple things. You could have like an ACL, access control list, and it will deny you if you're on that list, and things like that. We did some very simple things, right? Malicious people weren't that prevalent back then. In fact, we had trouble selling this because he said, like, who's going to really like DOS me? This was 2001, right? It wasn't. The more common thing is that you DOSed yourself by doing something foolish, right? But the world has changed, right? So if you look at just the past decade, there's just so much attacks going on. These are just news stories over the last several years. It's all about, attacking this site or that site or this web property. The amount of DDoS attacks happening and breaches happening, it's just mind-boggling, right? So the world has changed. And this is just some data. I can promise you this data only looks worse. I got this data 3 years ago. This shows sort of the attacks and how big they are, right? And as you can see, over the years, there are more attacks, And they're also bigger, right? So just to give you a sense, a DDoS attack of 500 gigabits per second is enough to bring down a small country, right? And over the last 3 years, it's gotten even worse. It's gotten into terabits per second, right? So this is kind of the situation we see where there's just a lot of attacks. And this if you've not seen this is called cyber extortion, where somebody is saying, I'm going to DDoS you unless you pay me in Bitcoin, right? This is an action law. I mean, we always, we don't want to, they're very ashamed to reveal who it is, so we always take that out. But this is the kind of thing that's happening, right? So edge defense has become such an important thing that just to protect the internet, you need to have edge compute doing the defense. So I'm going to give you some examples of that. So the first simple example I can give you is what is called a WAF, or a web access firewall, where you have some compute running on the edge that performs a firewall kind of action. Okay, so this is what it might look like. Somebody makes a request. The firewall actually can stop you if it thinks that you're malicious. Okay? So, I mean, in more detail, this is what it could do. It could do a series of computes. The first thing would be asking, are you sending things at the right rate? Right? The second thing, it could have a bunch of rules, right? For example, there are attack vectors, like, if you're doing cross-site scripting, which is a very common attack, or SQL injection, it knows what it is. It can use an attack. It can map it to an attack vector to see what, whether you should let you in or not. And more sophisticated is really reputation, which is really the analogy I like to give you is when you go and show your credit card, people know what your credit, what your credit report looks like, right? They know whether you're credit worthy or not, right? So one can build a very distributed reputation system where when you go in, you can actually look it up. Obviously that involves a lot of machine learning. You can see if this person is a bot. Is this person trying to attack you? Does this person have a past history of doing something bad? All of those things. So this is what a WAF looks like. This is a web access firewall. This sort of thing is implemented in metadata at the edge. Much more sophisticated metadata than what I showed you earlier, obviously, right? And another application of edge defense, important thing, is really bot management at the edge. This is sort of how many bots make requests to the Akamai edge, and we classify them as being malicious or benign. You can see that all of these things are going up, right? And in fact, I'll talk about this a little bit later. One of the downsides of AI is that it's very easy to create bots. And it's tripled. As of now, I think it's way higher. I think it's more like 150 billion bot requests coming into the edge, right? So what do you need to do with these bots? You need some intelligence on the edge that quickly classifies and manages those bots, right? So that is a computation that's running on the edge, where when someone comes in, you quickly figure out, is this a bot or not? If it's a bot, is it a good bot or a bad bot, right? There are good bots too. There are bots that just search your website, right? And they just spider your website so that a search engine can work. That's a good bot. You want to allow that bot. On the other, you have hacker bots that are trying to do something malicious, right? So you need a way in which the edge defense quickly figures out who's a bot and who's not, and whether this person is a good bot or not, and you can take action, corresponding to your classification. So this is what we call intelligent bot management at the edge. And this is what I was alluding to. AI has actually changed the world upside down in sort of the edge defense space. And it's changed it in a lot of different ways. And one of the ways it's changed it is that, we are seeing way more attacks at the edge on the internet. Because, part of it is that you can use an LLM to create a novel attack very easily. You don't have to know any sort of, you need not have done a security class or something, and it used to be that you need to be like a deep down hacker to do it. You can just get an LLM to do it, right? So people are just attacking the internet for all sorts of different reasons. And so, just you can look at the numbers, like the Akamai Edge had like 310 billion WAF attacks, web access firewall attacks. And bots, as I said, has gone up to like 150 billion. and 2 petabytes of traffic, attack traffic. So it's really become huge, right? That's one way AI has changed the world. A different and a more subtle way AI has changed the world is that you can attack AI at the edge. The edge has started to run AI. It has started to run machine learning models at the edge. And I'll talk more about that in the last paradigm, which is edge AI. But that means that edge defense becomes way more complicated because you now have, so these are all examples, these are actual examples of attacks. So, Bing chat spills secrets via prompt injection attack. So you have some things like prompt injection attack where you can prompt it the right way and make it spill confidential information. Or you can make it say the wrong thing, right? GM dealer's chatbot agrees to sell a Tahoe for $1, right? And if you are, companies are putting AI on the edge, and if you're kind of liable if you kind of say, if your bot, if your chat, your generative AI said that, this is what you would do, right? This is problematic, right? So one of the things that we are working on is actually what is called firewall for AI, right? It's very different from a WAF or a web access firewall. Web access firewall looks for things like, are you trying to SYN flood me? Right? That sort of a thing, right? Volumetric attacks and things like that, right? This is completely different. This is really to protect, you need some kind of a firewall at the edge to protect the AI that's running behind it. Okay? And this is actually a pretty interesting research area, how we would build that. So AI at the edge has brought in all these new kinds of attacks. There's prompt injection attacks. You can try to jailbreak what's on the edge. You can make it spill personal information. You can make it respond in a toxic way. You can make it hallucinate. AI denial of service is actually pretty interesting. You can actually make the AI do so much work that it can't do anything else, right? So all of these are just coming on, gangbusters into the edge, right? And really, how do you really build guardrails at the edge, right? You need guardrails for the inputs, for sure. You need guardrails for the outputs, right? And there are compliance issues, like if you are, if you said something, a server in Europe said something that is against the European AI law, and that's not compliant, the enterprise is liable, right? And it needs to happen in real time. One thing I should really note here is that all these firewalls, the really, really tough systems problem is that it has to be real time. Because nobody likes to wait, right? If you go to a website, I know there are some things that give you the spinning globe, but that's not ideal, right? It should just really happen, right? It should not degrade performance. So the performance security thing is always a difficult thing. Okay, so this is what I wanted to say about the first paradigm, which is really using scripting, right? Just running scripts on the edge. Now let's go to the next one. The next one is functions on the edge. As I go through these different paradigms, the difference between these paradigms is how compute is done, right? And what are the properties of that compute, right? And in the functions one, it's actually, you basically execute a function, and most of the time, it happens as a part of the web workflow, right? Most of the functions on the edge that we've ever built really add compute to a web workflow. What I mean by that is, let's say you're doing a transaction, you go to your bank, right? And you're doing a transaction, right? So there is a HTTP transaction going on, right? And functions as a service just adds compute to that transaction somehow. You're doing something as a part of the transaction, right? That is the paradigm, right? It's a very powerful paradigm, and I would say that it's very, very widely used. And let me say a little bit about that, right? So again, these things all have like a history to them. The first thing that we ever did that added computation to a web workflow was something called ESI, Edge Side Includes. Okay, we did that in 2001 and made it into a standard, right? The idea there was that you could compute the web page on the edge instead of getting it from somewhere else. You can assemble the entire web page on the edge, right? You can take the parts and just compute. So that sounded like an interesting thing for us because we don't have to go back to the origin provider and say, give me this web page and things like that. We can just assemble it on the edge completely, right? So ESI was really built for that. And this is an ancient web page. The web pages don't look like this anymore, but it used to look like this before. And this is built using ESI, right? If you look at this web page, almost all of this is cacheable, right? Except that little thing that says, welcome Rebecca, right? So I don't want to go back and ask for this web page when almost everything is cacheable, right? So this is something you can just assemble on the edge. So you can just use a little scripting language, which is executing a function of some sort, and you can just assemble it on the edge. It's a markup type of thing. Okay? This is really like the origin of this idea. Let me talk about something more modern, like 2019, right? We built something called Edge Workers, which is basically a very similar sort of thing. You have a web workflow. A client is actually asking for something from an edge server, and if the edge server doesn't have it, it goes back to the origin, and then it gets it from the origin, and then feeds it back. That's like a traditional web workflow, right? You're doing a transaction. You go to your bank. This is what it looks like, right? Now you can actually put some compute with every one of those events. So you can write a little bit of, you can write a Python program and say, whenever I get an on-client, whenever the client comes to me, that event will trigger that compute. So you can basically take the web workflow and you can put functions associated with every event, right? And this is what we call edge workers, where you can put JavaScript events associated with these workflows, okay? And you might also notice that if you put compute, you also have to get data, right? So that's what the edge key value store is. You need to build a key value store that can live on the edge for the data. So this is the idea of edge workers, functions as a service. And you can build lots of interesting things with this. I mean, people go crazy with it. Customers go crazy with it. You can build a waiting room function, for example, where you can simulate, like if you're a ticket master, for example, you want to simulate a waiting room where people are waiting to buy a ticket, right? You can do A/B testing quite easily with it. Just using this, you can use encryption, bot mitigation, failover. There's lots of things you can do just with this simple idea that you can take a web transaction and associate functions with them, right? Here's a much more recent and very modern, in fact, this is only like a few months old. Same kind of idea, but instead of having people write code in Python and doing all this stuff, why not use WASM, right? I think I've heard some talks about WASM in this conference. WASM is a nice platform where you can just write code. You can write code in pretty much anything that gets compiled in, Rust, Go, whatever you want. And then it's the same idea though. It's basically a function that you're writing, and you can associate those functions with the web transactional workflow, right? And it's very easy to deploy. So, I mean, I just gave you the deploy script here. As I said, when you think of edge computing, we are not thinking about something, like where to deploy it, how many, we are not thinking about any of that, right? The system takes care of it. That's the whole idea, right? So it's really literally two lines. You can just say, here is a WASM, bunch of WASM functions, deploy, right? The system takes care of it. It figures out where to deploy it. It depends on demand, right? And it runs on the edge. Okay, does that make sense? Okay. So I want to actually show you like a cool thing that we did in the summer. If you were at Wimbledon, in the morning we heard a little bit about conversational stuff, like conversational agents and stuff. This is actually a conversational application where you're sitting in Wimbledon. It's called match pointers. You're sitting in Wimbledon and you're watching a game and you want to know more about the game, more about the person playing there. Maybe you want to do some research on them, right? You want to compare them with somebody else, all of those things, right? So you can just talk to the application, okay? And it'll respond. That's what this application is, and it's an edge compute application. And under the covers, this is how it works. I mentioned that whenever you think of the edge, think of an outer edge and an inner edge, right? So the outer edge is the one that's like really huge, and it can give you really fast latencies. So the way this worked was that when a user actually wanted to, did something, it went to the outer edge for some basic processing. That's functions as a service, right? It has a caching layer also, because if you're asking questions that I've answered before, I can do a semantic cache and feed it back to you, right? So a bunch of these things happen using WASM at the edge. And of course, not everything is possible. You might be doing some really deep research on this player, and it's not possible to do it on the edge. There is the inner edge, which could host more heavy duty. Inner edge is something that with GPUs, and it can host something more heavy duty there, to answer some of those questions. So this is kind of what the architecture looks like, right? And it actually was pretty successful because we usually measure what is called time to first byte. So after you speak, when is the first byte that you received, and that was something like 10 milliseconds. Because I think most of the time the answer was coming from the outer edge. So this is an example of functions as a service. But also note that, these things are all used together. These paradigms are all used together, right? So it's not like this is just a function as a service, because this one uses both functions or function as a service and sort of the next paradigm that I'm going to talk about. Any questions? Okay. All right. Now I want to go to general purpose edge computing. General purpose edge computing is the most general thing you can think about. It's arbitrary applications that can run on the edge, right? So interestingly, we built that in 2002. In fact, we coined the name edge computing. And it used to be a trademark, Akamai trademark, till 2011. So this conference couldn't have been named edge computing without a TM there. But at 2011, a lot of other people were started to do edge computing, and we said, well, it's not giving us any particular advantage. Just like a Xerox machine is no longer measured, made by Xerox. So we kind of gave up that trademark in 2011. But this is how it worked. The idea was that you can run pretty much anything on the edge. You can take an application and you split it into two parts, an origin part and an edge part. And these were Java J2EE applications. You should remember that this was before the cloud. Edge computing was invented before the cloud, right? So this was 2002. AWS was 2006 or something like that, right? So there was no real cloud virtualization technology available, right? So this was actually built, using Java virtual machines on the edge, right? So I went back and I looked at some of the old, early adopters to this, and I have a few just for the sake of, just for the sake of looking at it. This was one of the early things that ran on edge computing. This was a contest that ran on the edge. Okay, and the benefit, of course, was scalability, because you can actually scale this to a fairly significant degree. Okay. And this is another one. This was the phone configurator, one of the very early adopters, where you had a phone and you wanted to configure it. That configuration could run on the edge. This was an example of offloading computation from clients. And this is actually a good one. This is actually a survey that ran on the edge back in 2003. This is really feedback from TV shows that are collected at the edge and processed. These are all really old examples. In fact, I managed to get the product catalog from the early days, and you can see that many of the computations that were adopted early for edge computing saw the same benefits as what we see in edge computing today. So if you look at these examples, it's either origin offload or it's client offload. Or it is, reliability. The basic fundamentals have not changed. Okay. So what is edge compute? What does general purpose edge compute look like today? So, in the olden days, as I said, it was JVMs. Now it's containers. So this is a product that Akamai actually released. This year actually is the managed container service, right? The conception is the same. You build a containerized application, and you hit deploy, and it gets deployed on the edge. Right? That's really what it is. Okay. So what could you do with it? So one of the things you could do with it is what is called IoT Connect. Right? So there are lots and lots of IoT devices, automobiles, applications, medical. There are more IoT devices than people, probably. And this sort of a thing is very amenable to general purpose edge computing. And, so one of the things you can do, because the edge is very, very close by, you can get fast response times, right? So one of the things you could do, and I'm just giving you an example here, is that you can make an IoT broker at the edge. So you can build an MQTT broker that can actually hook up devices, cars, and so on and so forth. For example, you could have cars talking to the edge and communicating through this broker, through the edge as a broker, right? They could subscribe to things, they can unsubscribe to things. All of these things could happen. So this is just an example of how you could use general purpose edge computing in this context. Okay. Now I want to talk about the fourth paradigm, which is edge AI. We've talked about scripting on the edge. We've talked about functions as a service on the edge. That's the second paradigm. And general purpose computing on the edge as a third paradigm, right? Edge AI, I think, deserves its own paradigm because it's actually driving a lot of edge computing today. And the basic idea is that you could do machine learning inference on the edge, right? In this picture, I show training to be in the cloud, but that's not always necessary. In fact, it's not always possible because if the training data cannot be shipped to the cloud, it has to be done on the edge also. But this is just a typical situation where the inferencing happens on the edge. And why focus on inferencing? It turns out that if you look at training and inferencing, the compute involved, we think that inferencing is going to be most of the compute, because you train a model and then you serve it to billions of people, right? It's sort of similar to content. You create content, and then it's consumed by lots of people. It's sort of like that. So that's why we focus on inferencing first. And what are the advantages of the edge when it comes to inferencing? Latency is a big advantage, right? So it has to be latency sensitive. But it also has a disadvantage, and which is where I think the research community can help a lot. As I said, the outer edge has low latency, but the resources are not there. We don't have GPUs there, for example, right? So that's one of the things that we need to really think about. Okay, so here's an example of a customer implementation of AI on the edge. This is an in-vehicle AI-powered voice assistant. Apparently, people like talking to their cars, and sounds a little weird, but apparently they want to do it. So how do you do it, right? So it's very latency sensitive, right? When you talk, the response has to come back very quickly, right? So that says, things have to be running on the edge for this application to happen. Okay, so this is an example of chatbots at the edge, which I think more generally is an important application. Okay. Here are just some other use cases. I just pulled out some other use cases for edge inference on the edge, and we can talk about these. I think we heard a little bit about how Adobe wants to make things conversational, right? We think that the entire web will be conversational, right? Nobody will be clicking and typing anymore, right? People will just be talking to the browser, and maybe it's not called a browser anymore, right? So that is the conversational web, right? And a lot of customers are actually interested in something like that. Let's pick a few more. Personalization and recommendation, again, is like a broad category of things that Edge AI can help with. It's basically the data is on the edge, and you need to have quick responses. So that is good. Fraud detection is another example. So you have transactions flowing through the edge, right? And if you want to pick out something odd or something bad is happening, you want to pick it out really quickly at the edge. So that's an example. AI-powered content generation, I already gave you an example of a chatbot. Real-time video understanding is also a very interesting application. One of the customers has video. Let's say you're in a football game, right? You have lots of cameras capturing lots and lots of things. right? You want to quickly pick among those 50 different cameras capturing 50 different things, the 2 or 3 things that are the most interesting and show it live to your viewers, right? So that's an example of something that needs real-time video understanding on the edge. Physical AI has to do more with using the edge for things like vehicles and things like that. So these are all some use cases, but let me put it all together. So I think what we've done is we've talked about sort of the history of edge computing, edge computing for the last 25 years. We've talked about different paradigms. I want to try and put it all together, and maybe talk a little bit about some research if I have some time as well. So as I said, when you think about edge computing and the edge, you really need to be thinking about these layers: an outer edge with thousands of locations, an inner edge with hundreds of locations, and a cloud, right? And what are the considerations? One of the most important problems is what to run where in the edge cloud continuum, right? You have an application, what do you run where, right? That's a very difficult problem. I say that when we first built edge computing back in 2002, we had to figure out what runs on the origin and what runs on the edge. Ultimately, that turned out to be the hardest problem, right? That's the reason why that edge computing offering didn't catch fire as we thought it would, because people were really not sure how to split the thing, right? But here you have this problem where you have this, you want to create, say, you want to create some experience, like the chatbot experience, right? You need to figure out where what should run, right? And there are many considerations. Latency is one consideration. Cost is another consideration. As I said, egress from the edge is cheaper from egress from the cloud. And it'll always be so, right? Resources, right? It's also a consideration. Where do you have the resources? Do you have GPUs, right? Privacy can be a consideration also, right? Because you may not be able to move the data from the edge to the cloud. It may not be possible, right? There can be compliance things, energy, all sorts of different considerations. I want to give you some kind of rule of thumb on how to think about this. The most performance-sensitive things tend to run on the edge. I think the scripting example that we talked about, functions as a service example that I talked about, usually runs on the outer edge. Anything that requires real-time response runs on the outer edge. If it's a lightweight AI inference, it runs on the outer edge, like in the match points example, right? The edge defense that I talked about, like the web application firewall, the firewall of AI, the new thing, DDoS protection, those things run on the edge, right? Why do you want them to run on the edge? Because you really want to stop any attacker close to its source, right? There are lots of compliance and legal kinds of things that would force you to run on the edge, right? For example, you cannot ship data elsewhere, right? We already talked about the cost, right? So what might run on the inner edge? I think the general purpose edge compute paradigm that I talked about, where you can have containers and arbitrary computations deployed into those containers, those things should run on the inner edge. And the inner edge is also where you could deploy GPUs, okay? If you need a lot of storage, that's probably the inner edge. A heavyweight inference, again, the inner edge. If you're going to use the AI inferencing software stack, that's also the inner edge. And of course, for even more resource and data and profiling, all of those things could run in the cloud, especially if they're not intensive, right? So this should give you sort of a, give you sort of a sense of what might run where, okay? Now I'm going to shift gears just a little bit and talk about some research that we're doing. So this question of what to run where, I think, is a very important question. So I want to mention 3 pieces of research. I'm shifting away from things that we built to things that are more researchy. And I'll mention just 3 and conclude it there. There are a few different ideas that we're considering for edge AI. The first idea is the idea of accuracy scaling, right? We published this in ASCLOS last year. The idea here is that you don't need the most precise and computationally intensive model to do something, right? There's a whole range of models that vary in the accuracy of the response, and the compute that they take. Okay, so we built a system that is actually sensitive to that and conserve edge resources. So this could be what the accuracy throughput trade-off looks like. Every point here is a model variant. They all do the same thing, but they do it with different accuracy and different throughput. Okay, there are some that are very accurate and have less throughput, right? And there are some that are less accurate and have high throughput, which means less compute, right? And we can actually modulate the accuracy within an edge data center so that when you have inference demand, when you're at the peak, you could use a lightweight model, and we are at the bottom, we can use a more heavyweight model. So this is what we call accuracy scaling. I mean, people commonly talk about hardware scaling, right? Which is adding more hardware or reducing more hardware. This is a different dimension called accuracy scaling. Okay, this is just a piece of research on trying to accommodate ML at the edge. The other thing we're thinking about is what we call model cascades, right? You may have two different models that do the same thing. One, less compute, less accurate. The other one could be more compute and more accurate, right? So you can put them in a cascade. So this is an example where this is a text-to-image generation model where somebody says generate the image of a cat. You could first feed it to the outer edge with a lightweight model. And if it works out, fine, right? If it doesn't, you send it to the inner edge with a heavier weight model. And what you need to do is you need something which we call a discriminator. That's what the confidence estimation is, that can look at the output and say if that output is good enough. Okay, so this is an example of how you could actually layer it across the edges. And this is a more complex example. This is something that we are currently working on, which is called a routed discriminator architecture, where you can have a router component that takes the query for generative AI, and it figures out what kind of model it needs. Does it need a complex model? Does it need a lightweight model? And then we can start with that, and then you can feed it to the right model, and then again check the output. So these are all ways in which you can conserve compute at the edge, right? And one thing I should note is that these routers and discriminators are all very lightweight components. They're themselves neural networks, but they're lightweight components, and they could actually run on the outer edge. So these are some of the things, as we build these things, we are actually thinking about some of these ideas. Okay, with that, let me just stop and, I think I've said a lot. I'll just wait for Q&A.
Use the mics on both sides to ask questions.
Great talk, and interesting to hear such a long history. Like this conference is the 10th anniversary, but we started 15 years too late. It sounds like your stuff. I'm actually going to ask you the question that I was originally thinking of asking the first keynote speaker. It's come up here as well. And so you mentioned the shift towards like the conversational interface. You talked about that too, as the difference between having a conversation versus clicking on lots of menus. And one thing that I think about there is like when I click a button on a web page, I do expect a response immediately. When I'm having a conversation, I expect the beginning of a response immediately, but sometimes it takes 10 seconds for it to speak back to me. And I wonder how that should change how we think about like performance of these systems and how this could affect scheduling, for example, of like I don't have to compute the full answer right away. I've got it's a 30-second response. I have 30 seconds to respond, even though I want the beginning to come right away. Do you have thoughts about how that shift in the model of our interaction might affect?
That is a wonderful question. I gave you the match pointers example, which was conversational AI that we deployed in Wimbledon this summer. We look at time for first bytes. That's the most important thing. So you do want that to be speed, but then you have more time later. Right? Interestingly, this is not a new concept because web pages also work that way, if you think about it. Right? If you look at a web page, we've always wanted to optimize what is above the fold. So when you look at a web page, there are things below the fold, right? We always look at time to first byte above the fold, and the rest of it we call. Right? It's a very similar sort of thing. that we focus on things like time to first byte, because you do have time for the lesson.
Hello, very nice talk. I'm Adarsh from KTH. So I have been working on this cascading and routing since last 3.5 years. Everywhere I go to present my work, I have been asked one question for sure. It's when you cascade models together, what happens is you have to run everything on the small model first, and then depending on the confidence threshold, you have to upload something to the cloud server or like a server, whatever you have in your setup. So there is a redundancy associated to that, and that redundancy becomes more and more when you go towards generative AI. For image classification, we have very good TinyML models, but for generative AI, there are not so many good models that can be fitted into, like, let's say, very small devices like MCUs and stuff. So
That's a great question, and that's the reason why we brought a router in here. So if you look at the router distributed model, the router tries to guess what kind of model is needed, right, in the beginning, so that you don't send everything through the line model, right? So, but of course, truth be told, both the router and the distributor are actually neural networks that we train, and it could get things wrong. But that's exactly the reason why we brought in the router in our most recent architecture, which tries to not send everything through the line.
one problem with the router though, sometimes the router can be actually heavier than the lightweight model that you are using on the device itself. I tried routing first and then I went on to cascading. So what happened is, even if you try, let's say, a simple classifier as a router, like SVM or stuff, that can be really computational heavy on the smaller chipsets. So yes, if you have a larger model,
You bring up a good point. This actually works only if the router and the distributor can be built to 1/10 the computational cost of the lightweight model.
yes.
And we show that it's actually possible in many cases. I can talk forward a bit.
If your task is like resource intensive, yes.
No, I mean, for example, for this task of text to image and text to video, we show that you can build a router and a distributor. So, but it may not be possible in all the applications, that I cannot say. But it is actually like somewhat ad hoc. If you can build it, you can use it.
Thank you so much.
Very great talk, very informative. I have a general question. So in one of the most recent podcasts, Elon Musk said that like his vision into the next, like in less than 20 years, phones, like the concept of mobile phones and mobile apps will pretty much change drastically, and like there will be no phone apps, and we'll just have AI, and like whatever you need, just ask AI. Like instead of touching your phone and like sending an email, for example, we'll just say send a signal to this person and like make this context, blah blah blah. I want to know like your vision in that, and also if you kind of agree with that vision, what part of that do you think, like what role does edge actually play in that future?
That's a great question. I mean, I think things are getting conversational, so I'm not surprised that people don't want to take and so on and so forth. I'd also say that the imagination actually has gone way beyond what we can build, right? This is one of those cases where customers ask about agentic AI, and like they have a lot of complex things that they want, but we are sort of still we're still like the bootstrap what we do. I mean, I can believe that would become that would be important, and I mean, I do think that some of it can run on the edge. It's similar to the example that we showed on the tennis application, where some of it ran as functions on the edge. Right? So we have to find that piece that runs on the edge, on the outer edge, and what runs on the inner edge, and what runs on the cloud. Right? So I think there are things that can run, and there are sort of like semantic caching and things like that can cache things semantically, so that you don't have to keep doing the compute work. So that's why I find this area very exciting, because there's lots and lots of things to do with research there, and the research is really lagging what people want in industry.
Ramesh, I need you to talk me off of the edge. Your talk was terrifying because I know the role that Akamai plays in cybersecurity and making the internet function. And as you were talking about edge defense, I suddenly got this anxious feeling, what if Akamai's infrastructure isn't able to keep up with the attacks that are going to come from these now super smart, multitudinous AI agents? Have you guys thought about that? Am I just freaking out?
Well, you're not freaking out. I think everybody is freaking out. It is a cat and mouse game, right? As I said, today's DDoS attacks are done using LLMs, generative AI, right? And done very creatively. Things that are novel attacks, are becoming extremely common because Gen AI can produce those kind of novel combinations of things that. So, as we like to say, we fight AI with AI. So we need AI on our side to fight, but there is no real answer to this because it is a cat and mouse game, and it will be for a long time.
Okay, great talk. Question about you want to see the perspective from Akamai on the real time, because you also mentioned the real time multiple times in this presentation. I think the system point of view is we think that 10 milliseconds is considered as real time. But in the last few years, we have been working on this autonomous driving. But with the autonomous driving community, what happening is they don't trust the edge. It's not because not kind of trust, it's because they don't provide enough, kind of real time, or the reliability, the level they want to use, they can trust. So I just want to get a sense of from your point of view that when do you expect that the edge is enough, so for the autonomous vehicle side that they can study into these resources.
Right. These are the edge AI use cases we're seeing, right? I think I put yours last there, which is physical AI. It's really the most difficult one because there is no room for error lots of the times, right? So, I've seen implementations. I showed you some implementations of AI for content generation for the Lubrica. That happens, the first byte is actually something that you like, just 10 milliseconds. The first byte. The edge was able to do quite a bit there. But physical AI, I think is one of the last frontiers in my own imagination because the stakes are so high and the latency requirements are so stringent. Right? We can never guarantee with any of what we have, we cannot guarantee latency. Right? So even with the tennis application that I showed you, on average it was 7 milliseconds, but there will be a few that are not. It has a long tail. Everything we do has a long tail. Because some queries might actually need us to go into the inner edge and execute a clear-weight model, right? So, but there is no room for those kind of long tails because the long tail could be a car crash. So I really think that to get that level of confidence from the edge, it's going to take some time. I'm not going to say it's impossible, but it is the last. I feel like that is one of the last frontiers here because the margin for error is so it's really bad. Okay.
Take one more question.
Roger Stefan Schuler-Donald. Thanks for this inspiring talk, and in particular thanks for your positive attitude towards edge computing. I was wondering, if I look around these days, right, I see that the telecom operators have more or less given up edge computing as a business. If I talk to people that say I work on edge, they understand edge AI, which for them runs on the device, rather than inner or outer edge, as you pointed out. So in that situation, I'm wondering, how do you see the future here? You say edge computing is now ready to be really successful, right? So is that going to take up as a business for you in the near future?
Yes.
Or what, and with which business drivers will it happen?
So all of these, already a business. A computer is already a business. I would say that it's one of the three core businesses that Akamai has. There is the usual content delivery business, and then there is the security business, and there is the computer business. So the business already is there. I think some of these edge AI use cases are not things you can just do on the fly. The kind of use cases that we talk about here, customers actually want to do them, actually, and I think there is actually money to be made in all of those boxes there, right? It's just that we have to build the technology quickly enough that it meets expectations. This is where I worry about, is that you build the technology quickly enough to meet expectations. Because with all of these things, AI running on the edge, just all of these things to be done. So my quick answer is that the business is there already, and people are willing to pay for it. It's just that we have to build the technology to make it satisfying enough that people actually continue to listen. I see a long way. That's why I'm excited about the research there. Because I think the research community can help. I think a lot of stuff.
All right. Let's thank our speaker.